All right. So without further ado, it's time to start the workshop. And the first session will talk about contact tracing systems. And we think that it is appropriate to start with a presentation from Google on the exposure notification API. Since most of the work we're discussing later in the day is building on top of that API, that makes sense. And we are fortunate to have Giles Hogman with us, who is intimately involved in this effort. So he is a director of privacy engineering at Google. He's also leading the Android privacy team and the security and privacy design of the Google Apple Exposure Notification API. So Giles will give the keynote for 30 minutes, and I will pass it to him.
All right. Can everyone see my screen, hopefully?
Yes.
Thanks very much, Athena, for the introduction and for inviting me today. So first thing I want to say is that despite the title of this session, exposure notifications, the Google Apple API and the system is actually not a contact tracing system. It is designed as a complement to healthcare authority contact tracing systems. And it has one very simple goal, which is to let the user know when they've been exposed to somebody who is COVID positive. And so I'm gonna go first of all into some of the design thinking and the design goals that informed our work. And then I'm gonna talk about how the system works and spend the second half of the talk on the privacy and security risks that we've considered. Before I go into the rest of the talk, I just want to thank all of the members of the research community who are in the call today for all of the input and the feedback that they've given us on this design throughout. There's no way we could have succeeded without you. I'm extremely grateful for all the collaboration and the input that you've given us. So, as I mentioned, exposure notifications has one very simple goal: to let the user know when they've been exposed. And its goal is specifically not to tell the user who exposed them or any information about who they were, the identity of the people they've been in proximity with. And it's also explicitly not designed to collect any information about precise location. And one point I'd like to make about the design principles here is that Athena mentioned we're all very familiar with trade-offs, and one principle that we've held to throughout the design process is that when faced with a choice of protecting social data versus protecting the infection status data, we believe that social graph data is much more sensitive than infection status. And we've obviously tried to reduce the risk of leakage of either of those, but if we're faced with any kind of trade-off, one of the guiding insights that we've used through this process is that social graph is more sensitive and more privacy risky than infection status data. Now, these are the privacy design goals that have guided us. And the simplest way to satisfy all of these privacy design goals would have been not to build any kind of contact tracing system at all. But we realized that we have an opportunity to help prevent the spread of the pandemic and get people back to work. And so we decided to do something with our platform to try and help the spread of the pandemic. And that brings with it several other very important requirements. One thing that we know, and that is obvious, is that the benefit and the impact of this system is related to the adoption rate, and it's not linearly related. It's there are network effects involved, so it's strongly dependent on the adoption of the system. And not only that, but we wanted to make sure that it's not only highly adopted, but not adopted by one particular sector of society, like users with expensive smartphones or the latest smartphones. One of the requirements that follows from that is that we know from our data that adoption is extremely sensitive to the use of device resources, and especially battery and network usage. So, for example, we know that in general, the install rate of an app is inversely proportional to the square of the battery usage. And so it's been very important to us to make sure that the system is making careful use of the device resources. And finally, I want to mention that trust in the system is obviously highly affected by the accuracy of the exposure notifications, and receiving an exposure notification is obviously a very alarming event for a user. And so it's very important, it's a very important requirement to have a low false positive rate. So now I'm going to go on to talk a little bit about how the system works. And before I go into the details, I just want to mention that this design, our design, has been very strongly inspired by much of the work that's been done in the research community. And if you're familiar with the D3PT proposal, our design is extremely close to that. And again, thank you very much for all the input that we've had from the research community. So a quick summary of how the system works. Every user of exposure notifications, their phone is constantly broadcasting a pseudonymous identifier that changes every 15 minutes on average. And we call those pseudonymous identifiers rolling proximity identifiers, and I'm going to use that term in this presentation. And so you might want to remember it. And at the same time, their phones are also scanning for the rolling proximity identifiers, the RPIs of users in their vicinity. So when Alice and Bob sit on the park bench for 20 minutes, their phones are both emitting these pseudonyms and scanning for pseudonyms in their vicinity. If Bob gets sick, he then uploads the broadcast IDs that he has been broadcasting for the last 14 days to a service that we call the diagnosis key server. And this is essentially a routing mechanism that publishes all of the known verified infected users' keys to every participating device. So when Alice's device receives the keys, the list of all infected keys, the device does a match between the set of known infected keys and the set of keys that have been observed around Alice over the last 14 days. And if there is a match, then it passes that information over to the healthcare authority app, which then takes the process on from there, warning Alice that she's been exposed, telling her how to get a test, etc. And also helping her enter the results of a test if she tests positive. One detail that I have glossed over, which is important to the privacy design, is that if you just send the rolling proximity identifiers, the RPIs, if you just publish those to every device in the system, that is extremely expensive in terms of bandwidth usage, and especially if you consider the sort of extreme infection rate design scenarios that we were thinking about at the beginning of the project. And so we've built this essentially a compression mechanism in where instead of uploading the raw RPIs, we generate 1 day's worth of RPIs from a seed in much the same way as a one-time password generator works. So we use a pseudo-random number generator to generate 1 day's worth of keys. And that provides approximately 100x compression rate. And this is very important in the realistic operation of the system. Another benefit of this is that it allows us to detect exposures of more than 15 minutes. So you can tie together, for known confirmed infected users, you can tie together 2 RPIs or to stitch together an exposure of more than 15 minutes, which is important from a clinical point of view. Wanted to say a few words about the division of responsibilities. Another very important design consideration was that we wanted to own the parts of the system that are really essential for the platform operator to manage. And that means the Bluetooth scanning, the broadcast of the RPIs, and the matching operation. And we are not healthcare providers, we're not healthcare authorities. So we wanted to be very clear that that we're only owning the management of the Bluetooth APIs, and the healthcare authorities are responsible for not only configuring the risk scoring that determines whether there was a match or not, which has clinical input, but also advising the user what to do when they get an exposure notification. So one thing that we found, we heard when rolling this out, trying to roll this out in the US specifically, was that state level healthcare authorities did not have, very frequently did not have the resources available to develop their own app and their own diagnosis key server and their own verification server. And so we addressed this problem by essentially providing exposure notifications in a box to make it as easy as possible for states to deploy exposure notifications. We provide them with a very simple deployment model where they fill in a configuration file, press a button, and we then generate an app, a developer account for the healthcare authority, and an instance in a multi-tenant diagnosis key server and a verification server. And just to note that both of those services are hosted by the Association of Public Healthcare Laboratories, the APHL, and using Microsoft Cloud. So it's Apple, Microsoft, and Google initiative. And this also, I want to note here that the ownership model of the developer account, the signing keys, etc., is all the same as before. So this is really just a way to facilitate the development process. And as part of this work, we've also produced a test verification service that we published as open source, and is also available in this multi-tenant service that we offer as part of EN Express. This verification service uses one-time codes and is designed to be as privacy preserving as possible. There is no, the diagnosis keys are not visible to the verification service, and no PII is used in the verification process. And you can see our design on our GitHub repository. Many people obviously are interested to know what the general adoption rates are for exposure notifications. So I've put a few statistics on this slide. We have more than 40 countries and regions globally that have launched apps using the Google, Apple exposure notifications APIs. Many of them have more than 20% of the population adopting. In the US, we have 12 states and territories that have launched EN apps, and 6 have publicly committed to using EN Express. All right, so now I'm going to move on to the second part of my presentation, which is a deep dive into the security and privacy risk analysis that we've done as part of the design. And again, I really want to thank the research community for all the input and the feedback that we've gotten as part of this work. We definitely could not have succeeded without you. And before I go into the details, I want to point to the risks and mitigations document that we published on GitHub. You can see the URL there. This is a very comprehensive analysis of all of the risks and mitigations that we've thought about in the design process. Today, I'm going to go into just 3 of the classes of attacks, just for time reasons, but we have five broad classes of risks that we've identified, and you can read about all of them in the risks and mitigations doc that I would encourage you to read, and we also welcome any feedback on that. We're very interested in hearing about new attacks and new risks to make the system as robust as possible. So as I mentioned, I'm going to go into 3 areas of risk that we've looked at. The first one is social graph leakage attacks. And as I mentioned this at the beginning, we believe that the social graph is probably the most sensitive data type that is handled by the exposure notification system. And so we put a lot of thought into thinking about ways that that social information could leak and how to defend against those. So the most important attack that we thought about is what we call a crafted query attack. And the normal mode of operation of exposure notifications is that the healthcare authority app downloads the keys, the diagnosis keys of all known infected users to the user's phone, and then it shows up to the API, the matching API, with a dumper truck full of diagnosis keys, and it says, "Hey, exposure notifications API, have you been near any of these? Please tell me the properties of the keys that you have been near that are in this set. But we realized that there's also an attack that you could perform where instead of showing up with a large dumper truck full of keys and not knowing which one of those matched, you could show up with a single key or a small set of known keys, identified keys, and say, hey, have you seen this key? And then using that attack, you could essentially back out the set of people that the user has been in proximity with. So we've built several mitigations against this attack into the system. First of all, we provide an audit log of all queries that the healthcare authority app makes, or the hashes of those queries, that basically makes the queries more transparent and any abuse more observable. Secondly, we require the diagnosis key server to sign the matching queries, which defends against a compromised app developer, because you can't inject keys through the app. Thirdly, we rate limit the number of matching queries to 6 per day to prevent sort of brute forcing using this kind of attack. And finally, we have strong policy limitations on the association of any PII with the keys. All right, the next class of attacks that I want to talk about is relay attacks. This is a classic attack in the literature that applies in many areas of security, but also applies into exposure notifications. And the basic idea is that the attacker gets hold of some RPIs that they know are going to be uploaded to a diagnosis key server and published to EN users in the next 14 days. And then they replay those RPIs to their target. And they could get hold of those RPIs in several ways, including, standing outside a test center and sniffing Bluetooth RPIs, or submitting their own TEK if they can get hold of a one-time password. So before I go into the mitigations, I want to start by saying that we believe that with this set of mitigations in place, these attacks are extremely unrealistic, and we have consulted very widely about the efficacy of the defensive we've put in place, including talking to Ron Rivest, who's not only one of the fathers of modern cryptography, but also an expert on voting systems, and the consensus we got is that these mitigations make the attack extremely unlikely and unrealistic. So what are the mitigations that we put in place? The first line of risk prevention is to make sure that the attack is as expensive as possible to the attacker. And the most obvious and cheap way of performing an attack like this is to use existing infrastructure and existing hardware, because deploying your own hardware is obviously very expensive. And so the obvious way to deploy an attack is to get malware onto a large number of users' phones, because smartphones are an existing Bluetooth broadcast infrastructure. And so we have put a lot of effort into making sure that our app store have very robust detection and enforcement against any large-scale deployment of apps that are using the EN UUID, Bluetooth UUID, and even apps that are just generally sniffing Bluetooth IDs. Second point I want to make on mitigations is that this attack is not as simple as just driving around replaying RPIs. In order to trigger an exposure notification, you actually need to be close to a user for typically 20 minutes. So that already adds a large cost to the attack. So in a way, the clinical properties of the design also are very helpful in defending against relay attacks, because you have to follow somebody around for 20 minutes in order to trigger a notification. Thirdly, the RPIs are bounded in validity, so they're only valid for in most countries for 1 hour, and so you have to relay the RPIs within 1 hour. Fourthly, I want to mention that these attacks are pretty easy to detect if, in the unlikely event that they did occur, a sudden increase in exposure notifications, which some healthcare authorities are collecting aggregate data on the number of exposure notifications. If you see a sudden increase of 10x of exposure notifications without an increase in the infection rate or the positive test rate, that's a pretty clear signal that something fishy is going on. And then finally, we also have the verification protocol, although I'll note that that is not a particularly effective defense against this attack, because you only need, because of the privacy properties of the system, you only need a small number of RPIs to perform the attack. We also looked at some of the standard mitigations against relay attacks that are in the literature, but for various reasons, they're not feasible in the exposure notification context. I'll just give you a couple of examples. So we looked at adding encrypted authenticated location to the RPI packet and excluding packets that were not transmitted close by, but that doesn't work because exposure notifications needs to work in public transport, for example, and the location can change significantly within a period of 20 minutes. We looked at distance bounding, which effectively uses the speed of light to ensure that the sender of the RPI is sufficiently nearby, or that the creator of the RPI is sufficiently nearby. But this requires specialized hardware that's not present in most smartphones, and a two-way protocol, which makes it infeasible. All right, the last set of risks that I wanted to talk about is wireless tracking risks. So using the BLE RPI and the BLE MAC address to track the user's location. There's two flavors of this. One is not without using the daily key, and in that case, the tracking risk is really identical to the standard BLE tracking risk, which is governed by the 15-minute MAC address rotation. And we don't think that the exposure notifications adds any tracking risk to the standard BLE system. And we've made sure that the RPI rotates on precisely the same schedule as the BLE MAC address to ensure that there's no additional risk. And I'm going to talk about one of the attacks on that in a couple of slides. But the more interesting one is the using the daily key. as I mentioned, the seed that's used to generate the RPIs does tie together for users who have reported as COVID positive. It does tie together the RPIs that are generated or emitted over a period of 24 hours. And as I mentioned, this is kind of one of the trade-offs that we've had to implement in the design because it reduces the bandwidth usage by approximately 100x. And it also allows tying together exposures of more than 15 minutes, which is important clinically. I do want to note, though, that the risk is limited to 24 hours, and that this period of 24 hours was selected early on in the design process when we consulted epidemiologists to sort of figure out the worst case infection rates that we should be designing towards. And what we know now is that in many countries, the infection rates are considerably less. And so we are considering adaptively reducing the rolling period to reduce this risk, but we are still working on the interoperability of that change. All right, as I mentioned, there was an attack reported by Serge and Martin on the Bluetooth rotation part of the design. And the way this attack works is for a set of phones, the MAC address and the RPI actually were found to not rotate precisely in sync. And there was a period of about 200 milliseconds where there was an overlap. And this allows you to bridge between RPIs. We have, after we got this report, we have rolled out a patch which basically delays the RPA rotation to give the MAC address time to catch up. But I do want to note that we don't think this attack is particularly valuable for an attacker, because in order to carry out the attack, you have to be present at precisely the point in time when the RPI rolls over. And if you can do that, you're basically following the user around already. And also, if you're present at that point in time, there are many other ways that the MAC address could be bridged. And that is not, for example, using the signal strength, that is not the threat that MAC address rotation is designed to protect against. I wanted to say a few words about telemetry. I know I'm running out of time. We've taken a very strict approach to minimizing the telemetry collected by the exposure notification module to strictly what's required to make sure that it's not crashing and that it's operating as intended. We strip all identifiers from the telemetry logs before sending them off the device, and we've put a lot of effort in to remove any logs that could be used to derive healthcare information. For example, we don't collect events where the user uploads their diagnosis keys. I do also want to mention, because there's been some confusion around this, that whether or not exposure notifications is installed and operating, the Google Play Services, which is the release vehicle for exposure notification, collects information that is used to ensure the safe and secure operation of the Android platform as a whole. So, for example, battery usage, crashes, memory usage, managing information used to manage updates, etc. Those are all collected by Google Play Services and are essential for the operation of the device. But we do provide user control over the usage and diagnostics data that we collect. And similarly, Exposure Notifications Express, EN Express, collects some diagnostic logs to make sure that the system is working. And we use an open source de-identified logging system called FireLog for that. That's all I had. I wanted to just give you a few resources to follow up on to finish up. So we publish source code and a detailed description of all the telemetry that we collect and the risks and mitigations FAQ that I mentioned earlier. Thank you.
All right. Thank you, Giles. There are several questions for you on the Q&A. Maybe you can take the time and answer to them directly there. I will not ask you these questions now, but I will move on with our next speaker, who is Pablo Rodriguez. So Pablo has had different stages in his career and has been involved in privacy for a long time. Today, he is joining us with in the capacity of being involved in the National Contact Tracing app in Spain. Pablo is a member of the AI Ethics Board for the Spanish government, and he has been a technical expert, a consultant for them for the deployment of the national app. So thank you, Pablo, and sorry for cutting into your time.
Oh, sure. Thank you, Athina, and thank you so much for giving me the chance to reconnect back with this community and show some of the progress of bringing the work that has been happening over the last months into reality, and sort of what's been happening in Spain and the pilot that we run as a showcase of how these tools are being deployed in the ground. I mean, I have to admit that it's been a tremendous effort of innovation and research at multiple layers, from using Bluetooth to do exposure detection to at the layer of the epidemiologists, and the epidemiology world had to move very quickly into this digital space and define what are the terms and conditions that would make this tool work, and in terms of privacy, where this privacy first approach that has been pushed over the last decade in Europe has crystallized into a very into fantastic effort across different countries in Germany, in Switzerland, in France, proposing solutions, and then Apple and Google adopting the DP3T approach for privacy by design. So now that is one part of the equation. The other part of the equation is the fact that these tools are meant for saving lives in the middle of a pandemic, and rolling out these systems countrywide while the pandemic is going on is something that it's a big undertaking for most countries. In Spain, we took an approach where we wanted to better understand the efficacy in terms of epidemiologic results and how it's going to be received by the population, and we came up with a control pilot, a control experiment out of the Spanish app, which is called Radar COVID. And this is what I'm going to talk about today, and share some of the results of this pilot that happened in the middle of the summer. The first thing that I wanted to talk is that we sort of took an innovative approach to trying to see what is it that we wanted to, what was our dashboard for metrics to understand what success would look like. And we thought about this effort that we're doing almost like a moonshot, you know, something that is very important to happen, but it's very hard to achieve. And And our moon, so our aim was trying to flatten the epidemic curve, keep it there while avoiding the socio-economic breakdown that happens if you lock people in their houses. And there are multiple shots that you can take at it from, antiviral therapies or new vaccines. And the one that we're talking about today is these digital contact tracing tools as a radically different way to control the transmission chain. And we brought together a number of experts from multiple disciplines and try to anticipate what would be sort of the killer questions. So the questions, the reasons why everybody would tell you, oh, this thing will fail because the tracing efficacy will not be there, the adoption and the retention will not be there, people will mistrust it, interoperability will not happen, and so forth. And then being able to follow these metrics on with experiments that we were throwing and trying to see how confident we were before the rollout. The pilot design happened during the month, the duration happened during the month of July. We wanted to have at least 2 weeks of app activity, and it happened in an island, in small island in the south of Spain, in the Canary Islands, the island of La Gomera. Totally has about 10,000 people, and the capital is San Sebastian with about 8,000 people. The participants were both locals as well as tourists and roamers that were coming from a nearby island, either through boat or through by airplane. And it was at the time where the epidemic curve had come down in most of Spain. So we simulated an outbreak. So we simulated infection in the different mobile phones, and the alerts were based on the proximity, 2 meters, less than 2 meters distance, and more than 15 minutes. And these infections were being activated after a given incubation asymptomatic period. The rest of the system, we involve the local authorities and the health authorities to simulate as much as possible the real deployment. So with a dedicated health call center that would handle the alert users and so forth. And there was an aim to do both quantitative efficacy analysis and qualitative users groups research to provide probably one of the first real studies of the efficacy of these apps once they get to a significant level of adoption. We try to understand these parameters from a citizen behavior point of view in terms of commitment, retention, adoption, in terms of operational indicators, the effectiveness and the reaction time. Reaction time is super important to try to cut the transmission chain as quickly as possible, and in terms of the rating, usability and perceived effectiveness from a user point of view. So I was saying that the pilot started 29th of June, ended 31st of July. The first week, we trained the personnel and we did the campaigns in the island, and then people started installing it, and we had multiple waves of the simulated outbreak at different times during the month, including people that exploring different mobility patterns from people that were coming by boat or tourists that were coming by plane to try to mimic as much as possible the realistic setting of a day-to-day in the island. There was a lot of involvement from the local authorities, installation points where people were helping elderly or provide answers to how the app would work, because it's something that is, at the beginning it's a bit confusing. People think that it's going to give you a heat map, or that there's going to be geolocalization. So none of that is the case, and it's a very privacy preserving tool by design. So there was a lot of information happening for people to adopt the tool and participate in the pilot. during the pilot, we released a number of versions, making improvements and also calibrating the Bluetooth settings. So so we would get the proper set of indicator of contact tracing. And I'm gonna jump into some of the results. As I said, in the island, about 10,000 people living there, more than 3,000 people downloaded. We simulated an attack rate of about 10% of the participants, so about 349 secondary cases were created, so as fictitious infected cases. Out of those, we had about 213 confirmed cases, so compliance rate of people participating after saying that they were going to volunteer in the participation was about 61%. And those generated a number of alerts that then a percentage of them, around 10% of them, went and called into the call center to finish off the pilot, and from there on they would be taken by in the real situation by a manual tracer that would do the proper interview and calibrate the level of risk of that exposure. The pilot results were in general fairly positive. The level of adoption was favorable, so more than 32% of people in the island adopted the tool, and this tool that doesn't have linear effects, has network effects, so it's important that you have a peer-to-peer behavior and enough density of people downloading it for it to provide the expected results. There was a good retention of the apps, people using it, so more than 80% of people continue using the app after the pilot finished. And we saw a good compliance of users with reporting their infectious level. So even we need to take this with a pinch of salt, because again, it was simulated, but 61% of people reported it, and those ones that reported it did it. 78% of them did it in less than 24 hours. Out of those, about 12% of them called the call center. This is a figure that we expect it more. It's a bit low. Wondering whether it had to do because of the simulated setting, and people thought, well, why would I call if at the end, I'm not infected? And it would be nice to evaluate in the real deployments what is this value, because it's important that we bring people into the health system, so they complete the evaluation by the health authorities. Although another interesting effect that these tools could have is that even if people don't engage with the health authorities, there is a sort of a change in behavior. Somebody receives the notification, and maybe even if they don't go through the health authorities, they end up changing their behavior, and they will not visit a population at risk or relatives, or not travel. But that is something that is still to be confirmed. We couldn't gather enough evidence to support that validation. And one thing that is important is the efficacy, especially compared to manual tracing, even though this tool is not supposed to replace manual tracing, but be a complement to them, because it's supposed to see a higher number of contacts, and contacts that are not near contacts, but that could be blind to a lot of people, because there's not people in your near circle of friends or work. What we noticed is in aggregated, we saw that the number of alerts generated per infected case was about 6.4. In the Canary Islands, the average report of close contacts discovered by a manual tracer is about 3.5, so it's roughly doubles the the efficacy of exposed contacts versus manual tracer. And through interviews, people estimated that about 25 to 30% of the reported alerts probably came from people that they did not know. So people that were not playing the role of an infected case. And that's important because those are the types that a manual tracer would probably not be able to detect. We also ran focus groups and user feedback. We interviewed about 90 people, and the results were positive. You know, about close to 8 out of 10 people said that they got a good sense of privacy and anonymity in the tool. 9 out of 10 say that they recommend to others, and about 70% of people, they say that they'll rather get alerted by an app than a person. And 100% they said they would continue using the tool after the pilot. So with all this information, we provided a positive recommendation for launch, and there was an intermediate launch in Spain on the 15th of August and a national launch on the 15th of September. Now it's about more than 4.5 million downloads and integrated in most of the regional authorities in the country. And I think that the jury is still out about the ultimate efficacy of this tool. I think in different countries there are different levels of deployments, but I think this is a terrific journey of innovation, of digitizing part of the health sector in the middle of the pandemic, and a tool that is definitely very welcome in this time. So with that said, thank you so much, and thanks for hearing, and happy to answer later any questions. Thank you.
All right, thank you, Pablo. Thanks for staying on time. There are a few questions for you in the Q&A, if you want to go and answer some of those. And I encourage people to post questions for the speakers in the Q&A. Our next speaker is Ramesh Raskar, who is an associate professor at the MIT Media Lab and the founder of the PathCheck Foundation. He has been very enthusiastic about putting the community together and open sourcing resources for COVID. And today he's going to talk about a hybrid manual and digital contact tracing approach. Thank you, Ramesh.
Thank you, Athina. Wonderful to be here. Yes, I'm Ramesh Raskar at MIT and also founder of the PathCheck Foundation. Today I'm going to talk about privacy-preserving machine learning for split learning as well as contact tracing. We encourage you to go to our website, pandemic.mit.edu, or join our Slack channel, tiny.cc/pathcheck Slack. So we've seen this utility privacy trade-off in many slides. On the horizontal axis, you know, anonymization, obfuscation, or encryption are mechanisms that we often use for privacy. But two techniques have emerged in the last few years: federated learning from Google and split learning from our group at MIT. And these techniques allow you to not only conduct statistics or inference, but also full-fledged machine learning. And the idea behind these techniques is to share wisdom without sharing raw data. Specifically, when it comes to exposure notification and case management, you know, you would use a smartphone-based proximity. Then step 2, notify if you have cross path, and make sure you can do that with privacy and speed. On the smartphone, maybe provide solutions for self-assessment or self-diagnosis. And then finally provide solutions for public health and business coordination tools. And the challenge with a lot of smartphone-based approaches is that although it does a reasonably good job for step 2, it actually does a very poor job for step 3 and 4. So it can alert an individual, but doesn't help as much the public health entities or businesses because they don't get a dashboard view of what's going on. And if you think about the experience of an individual through COVID-19, it's not just the getting an exposure notification that they may have been exposed, but they have to do a test, they have to monitor their symptoms, they have to test, see if the tests are positive or negative, quarantine for 14 days, at some point, you know, resume their daily activities, and so on. So it's a pretty complex process from an individual's point of view. And we think smartphone-based solutions can really make a difference. Of course, any large software company could just come in and deploy this solution. The challenge is, how do you achieve this in a privacy preserving way that uses distributed computing at every stage? And that's why the presentation we heard earlier today, brings in all these issues of security, privacy, inclusivity, misinformation, fraud, and so on, because pandemic, in a sense, is not just a technology problem or a biology problem, it's really a social problem. So we launched a project called MIT SafePath with the NSF rapid funding. And so we appreciate the NSF support. And after working on that for some time at MIT, we launched a nonprofit called PathCheck Foundation. And over there, we're solving this two-sided problem, the app problem, as well as the dashboard problem. And in that sense, we're agnostic to what specific proximity APIs one can use. In fact, we have mixed opinions whether Bluetooth is actually the most secure ways to do it. We think actually GPS, if done right, is more secure and more private for contact tracing. Nevertheless, right now we are focused on using the Google Apple exposure notification protocol. It's a spin-off from MIT, and we are looking at digital pandemic response in general. In first stage, it's about helping states and nations launch their exposure notification in case management apps. We already have contracts in multiple US states. Some have already launched, like Hawaii, Guam, and a few others. And then we have a few large US states that will launch in the next few days as well as few European countries and LATAM countries that are using PathCheck Foundation code base to launch the app. Very quickly, it has become the world's largest open source nonprofit project for COVID-19. It's just an amazing community of professionals. And the foundation itself has several professional volunteers as well as full-time engineers. And we are very fortunate to have millions of dollars in philanthropic funding to make it happen. So the apps are available on App Store and Google Play. And again, welcome to participate on GitHub and on Slack channels. And the foundation itself, continues to provide open source, open standard, free software for anybody, in addition to training and server training and alliances that's on the left. But certain states and countries just want a professional solution, a white glove service. So the nonprofit also provides a professional service for a full-fledged app and website and server launch, app maintenance, server operations, and so on. So it's kind of a two-sided, two different entities. One purely on the open source, open standards, and the other runs like a software company. And the reason why we think is taming this pandemic is not just about exposure notification, is that we have many challenges listed here on the left. Test verification, behavior, connection to manual contact tracing, integration with testing, many rich insights, and they require a lot of innovations that many researchers and scientists on this field would love to work on. It's just that it has never been deployed at such a scale, and that's why we need this open source, open standard platforms. I won't go into the detail, but we can have a conversation about this later on. And because of that, as we said, we have mixed opinions whether Bluetooth is the right solution. We think even if it's Bluetooth, the payload of the Bluetooth, which is what's broadcast between two phones, actually can be very rich. For example, the Bluetooth payload broadcast can include additional context like which phone, which GPS location, are you wearing a mask, all those things can be embedded as part of the Bluetooth payload. And we have published a series of papers, including using low entropy signals like GPS and Wi-Fi and how they can be used for collocation. Also, it's not just about forward tracing, but it's also about backward tracing. And it's also not forward tracing with just one hop of exposures, but multi-hop of exposures. So, we have papers that are about 4 or 5 years old in this space. So we have cleaned it up and published it again in the context of COVID-19. We continue to believe that GPS is going to play a very critical role if we can just change the protocols, because today's GPS is considered basically a second-class citizen on smartphones. But if it gets the same prominence as Bluetooth, we think GPS is actually even more secure, even more private, even less hack. It's even more hack resistant than Bluetooth, because in Bluetooth, you're constantly emitting a signal, I'm here, I'm here, I'm here. But GPS is a completely passive way to say what's going on. In addition, we think it's not just about exposure notification, but a lot of the data on your phone, questionnaires, sensors, your prior health history can be combined to provide the solution. So that's why we have a technique called split learning for distributed private machine learning that we think can be used. And very recently, we published a new paper for a technique called splintering, which is inspired by multi-party computation, but instead of requiring multiple servers, 2 or more servers, all the operations can be done with a single server. So single client, single server, but a smartphone can create splinters that all go to the same server and get the services it wants. So please check our website on all the research in this space. Very briefly, to give you an idea about how split learning works, a typical centralized algorithms would suck up the data from all the edge devices like hospitals or smartphones and train the machine learning algorithm, let's say to detect pneumonia from chest x-rays. Federated learning would do that by using partially trained models and effectively average them and go through multiple epochs. And split learning from our group at MIT actually converts each data point into a feature vector, and only the feature vector is shared with a server. And of course, the beauty here is the feature vector, we smash it in such a way that the original data cannot be reconstructed. Not just personally identifiable data, but you cannot reconstruct the original data in any reasonable way. So that's why we call it smashing, this smashed wisdom. And it's implemented with what you would imagine, which is early layer of deep neural networks are executed on the clients, and the later layers are executed on the server. And the smasher, which is what converts data points into a smashed feature representation, is where all the magic comes in. And we have techniques based on a distance correlation that reduces the distance correlation between the data point and the smashed representation, but it's good enough for inference or training. And as you can imagine, any decentralized computation has many challenges with respect to compute and bandwidth and memory and machine learning accuracy and so on. And this just becomes a very rich area for research. And the one marked in red are probably some of those pesky issues. So the good news is that split learning, as compared to other techniques like federated learning or SGD, is dramatically better in terms of compute, bandwidth, and accuracy. And it works especially better for heterogeneous data and when you only have few entities that are coordinating with each other. And we have shown that on multiple medical imaging benchmarks. And we think a scheme like this that allows you to use data on your smartphone for health applications, although every phone, although the number of phones participating in this process is going to be very few, and also they could be offline as opposed to federated learning, where there could be going back and forth. There could be multiple epochs, a lot of communication. We can use the split learning methods. So to conclude, I think a digital pandemic response is more than just exposure notification. It requires privacy-preserving machine learning. So hope you'll join us at pandemic.mit.edu for this large open source, open standard effort that's going on. And please join our Slack channel as well. Thank you.
All right. Thank you, Ramesh, for an interesting presentation. There are a lot of questions for you in the Q&A, so if you can go and answer them one by one, it would be great. All right, and the last speaker for this session is Sharat Mehrotra, who is a professor at UC Irvine. He comes from a database background and he has been working on related problems for some time. And recently his systems found a killer application for COVID purposes. His technology is different from what the rest of the panel discussed. So he's working less with Bluetooth and more with Wi-Fi and other sensor data. So Sharat?
Thanks. Can you see my screen? Okay, very good. Thank you. Yes. So I'll give you a small talk on what we've been doing in the context of the TIPPERS project, which is a DARPA-funded project for creating a smart space at UCI, which serves as a privacy testbed. Before I do this, since I realized that this was an NSF-funded workshop, so I wanted to sort of pitch a little bit a different tone. And also this will probably create give you a sense of why this project that we are working on in terms of COVID is different compared to contact tracing. So we had worked for about 8 years or 7 years for a large ITR project called Rescue, the goal of which was to bring transformational improvements using information technology to crisis response. Now, most of the work we had done there, which sort of got transitioned to a variety of different places, was on response technologies. But there are some lessons we learned which are sort of different, which we had not started off with when the project started. One of the things that came across was that critical, as compared to response, preparedness and prevention is actually extremely important or critical in any kind of crisis management. Another was that while we normally think of crisis and we think of federal agencies, state, local agencies sort of fighting your crisis, actually the organizations and individuals play a very, very large role in being the responders themselves. So you have to sort of consider that. Another thing was that any technology that you design, I think Giles covered this quite well in the beginning of the talk in his keynote. Affordability and actually the fact that you reach all sectors of the people is sort of critical for any technology. So it's a key to adoption of technology. And if you think of affordability, you can sort of think in terms of monetary costs as well as societal costs. So for example, privacy will be a very critical societal cost. If giving up on privacy will be a very critical societal cost if one has to pay that. Okay, so with that background of the work we had done, so let's get back to COVID and the work that we are doing now. So if you look at, let's say, the technologies that are being discussed today and given the context of this workshop, we are mostly focusing on contact tracing using Bluetooth, RFID, and Ramesh made a case for GPS, etc. And the way I would look at this is that this is post facto, it's a response activity. Like sort of you're trying to find out after the event has happened, in this case, the spread of the virus has happened, you're trying to track people down. Another set of technologies that you could consider is, and the question you can ask is, can technology be designed to help prevent the infection in the very first place itself? And if the answer to that is yes, where would we place those technologies, which will actually be then meaningful from the perspective of prevention? And furthermore, can they be done at a very low cost? Because cost is critical in this kind of setting, as well as is there going to be a low barrier to adoption of such technology? And sort of if we think a little bit more along this direction, let me see if this works. Okay, it does not. Okay, let's try this. All right. So prevention, one of the things that we have been told is masks are one of the most important things as far as prevention is concerned. The other thing is social distancing. Mask is like, you now need to go towards visual computing and so on, but at least for social distancing, we can do this based on location and on occupancy and so on of people. So monitoring adherence to social distancing becomes an example of, let's say, how we can do prevention. Where would be where the most of, let's say, the super spreader events actually happen? Usually it'll be things such as stores, malls, workspaces, gatherings, all that kind of stuff, right? So organizations can play a very critical role in this setting. Very low cost. So the system has to exploit an existing sensing infrastructure. We cannot bring in fact, almost every technology we are considering is based on the same thing, because everybody carries cell phones or smartphones. Most of us carry smartphones, so they have a built-in sensing infrastructure. So we cannot avoid, we need to sort of exploit the existing sensing infrastructure instead of putting new stuff there. And the last part, which I want to bring in, which is sort of different, is low barrier to adoption. So if you think of, let's say, cell phone based or basically Bluetooth based or even GPS based mechanisms, people have to opt in, or they have a mechanism, they have to sort of actively participate in the collection of the data. The other part of sensing technologies are passive technologies, where data can get collected in the system automatically without necessarily the interventions or any particular, let's say, explicit permissions from the user. Now, users can opt out, but most of the times they're by default opted in. So an example of this is going to be Wi-Fi, and that's where I'm headed towards. So the point is that this has got very high rate of adoption. All right. So with this thought process in mind, what we did at UCI was we started off with Wi-Fi basic data. So every time you connect into and come into the campus and connect to the Wi-Fi networks, there's Wi-Fi events that are generated. Specifically, the events that were we used or we have used in our system is connectivity events. So what the Office of Information Technology that maintains the Wi-Fi infrastructure at UCI, what they do is they pass these events to us with appropriate, like we build the software for them to sort of scramble it. We don't necessarily get all the exact, let's say, connection events. We randomize basically the MAC addresses. And this comes into a system which is Tippers, which is the one that we have built. And this can support a variety of different applications, in particular for basically applications of relevance to COVID-19. Okay, here are examples of it. So one thing we can do is social distancing. So the way we interpret social distancing is more towards occupancy. So what's the real-time occupancy at different levels of spatial granularity? And we go all the way up to room level granularity. And the main point being that we'll promote interventions and behavioral changes. If people are congregating a lot in some places, then sort of we can find that out. Another is cloud flow. What are the regions where there are a lot of people who have been sort of passing through? So this can, for example, help give alerts to vulnerable populations, schedule cleanings. And then also, we do have information about people and who came in contact to whom at the course level, which can help us identify basically exposure regions. Where are the regions that are sort of exposed in space and time? And once we have that, we can also have exposure tracing, very much like the way one would do it for the Bluetooth. We can also do this based on the proximity gained from the Wi-Fi itself. And of course, this mechanism can be coupled with the Bluetooth mechanism as well. So it's complementary in that sense. So what Athina wanted to do was to give a short demo. So I'm going to try and see if that works. And Athina, let me know if this actually plays out in your screen or not, okay? So here's an example of some of the tools that we have built, which are in use. So this is the, let's see if it works. Yes, it does. So this is the live map of occupancy at different parts of the campus in different buildings. So as you can see, if you look at this, there is a building called Khalaiti 2. Can you see this, Athina? Is that visible? Hello?
Yes, it is visible.
Very good. All right. All right. So here are the occupancy levels of different places and different parts of the building. So there are different regions here. They're not necessarily semantically named, but this is, let's say, the atrium area. And there are 3 people right now out there. And it's sort of close to empty as a percentage of capacity. So you can sort of get this. This Bren Hall is the computer science building. And let's see if there's anybody there right now. Okay, no, actually Bren Hall is more or less empty right now. Frederick Ryan Hall, and so on and so forth. So actually this place is sort of interesting. There are about 6 people in the Natural Science building. So you can sort of have a tool which is dynamically sort of addressing this. Actually, it gets interesting if you see this. Now, to get a sense of how useful this tool can be, just the occupancy part of it, here is, let's see if this plays out. Okay, this is the occupancy map. Basically, say I could have basically gone to the different dates in the previous screen. This is a shortcut to the same thing. So this is the display of the buildings on March 12th before, I think March 12th, 13th was the day in which the campus decided to sort of notify people that we should not be, there was a lockdown. Around March 13th is the lockdown date. So this is a day prior to the lockdown, and you can see that a lot of the buildings are sort of very heavily occupied on this day. And just to show you the example, what happened on March 19th, let me click here. This is after the campus said do a lockdown. And if you see, there'll be a dramatic difference in the occupancy levels that will show up. So if you notice that all of these things are green, so there's still a people in Khalaiti 2 building a little bit more than what one would want, but mostly the campus started getting empty, more or less at this stage. So you can sort of get a sense of monitoring something like this can be extremely useful for management or understanding of the, let's say, the management of the buildings and spaces in the context of even of recovery. So let me show you one more, and oops, sorry. Let me show you one more. The system we have is actually being used, if I can get the cursor correct, yes. So it's actually being used right now in Bren Hall. So it's been adopted as part of the campus reopening strategy. And this is the display that basically the computer science department uses as part of its plan for monitoring buildings and so on. So like whether the occupancy levels are low or high or whatever. So actually right now, if you notice, there's a live map. So in the ICS2 building, there's in floor 2, there's a medium level set of occupancy. So you can sort of get a sense of through a dashboard as to what the occupancy levels are of the building. All right. The thing that's basically powers the system is a system called Tippers we have built, which is a scalable data management middleware for sensor-based applications. And Tippers has been built with privacy by design principle in mind completely. So there are several components to Tippers. Of the different component, which includes scalability in terms of data management, mediation technologies to store stuff in different places, abstractions to sort of bridge gap between sensors and physical world. But the one that's sort of interesting from the perspective of this workshop is the technological PIoT, which is privacy enhanced IoT system that we have designed. And what it is a verifiable policy-based control the sensor data streams. And essentially imagine data streams coming from sensors, and you can apply a variety of different technology, privacy technologies to it, whether it be differential privacy, you can do encryption, you can do randomization, and so on and so forth. All right. So that's the one that powers the system. If we look at Wi-Fi based, let's say, mechanism for building tools for tracking people or occupancies, there are several obstacles that come into play. One of the first question that comes into play is that in the case of Wi-Fi connectivity data, where you're locating people based on the distance from, or based on the what Wi-Fi access point they connect to, basically the localization in both in space and time can be actually very coarse, and this can lead to high level of false positive and negatives. So that's one of the first obstacles that comes into play in sort of building the system. And one of the things that we did was use machine learning techniques to sort of do data cleaning, which actually, the more context you give to the information to the system, the higher the accuracy levels you can achieve. So we have a system which we sort of built, which achieves around 88 to 90% accuracy up to for room level localization. So effectively, we can sort of figure out from the data what rooms people are in the accuracy level of around 88%. The second concern that comes to play is the privacy concerns. So now notice that in this particular case, we are actually only using Wi-Fi data, which is actually already getting collected by the Wi-Fi network. So one may sort of wonder, why is there a privacy concern given the data university already or organizations already catch or collect such data already? The problem is that unlike the data that collected by the Wi-Fi protocols is intended for creating a Wi-Fi network and providing Wi-Fi services and not for locating people. And if you sort of start looking at the different purpose for which you're going to use the same data, then privacy concerns naturally arise. So one of the very first things we did when we started working on this thing a few years ago was we did a sort of a study to understand how invasive can let's say Wi-Fi signals be. And in this example, I'm showing the capture of Wi-Fi signal, but anonymization. So these signals are anonymized. They're also periodically randomized as well. Despite that, with appropriate machine learning techniques, you can pretty much learn all the events that happen in the building. You can develop mechanisms to classify people into visitors, passerbys, residents, faculty, staff, so on and so forth. You can also learn social networks. You can get to sort of learn who hangs out with who, or how many, what kind of site, in which region. So there's a lot of information which you can basically glean from the Wi-Fi signal itself, which could be significantly privacy violating. And why is that even a concern? So here's a simple example we used, one of the very first things we did. So imagine that I'm tracking faculty and I'm trying to figure out whether they come late to classes or not. So even though the data is fully anonymized and data may be randomized, I can still sort of decipher that this is Athina. Since I know the class schedule, I know what time she arrives to her classes, and we can then sort of have all kinds of different studies which are sort of very invasive, which people will consider pretty invasive. So there is a lot of impact of, let's say, a technology of this kind. And that's where privacy was a critical aspect of building in a Tipper system itself. So here's an example of basically, so I'm not going to get too much into the details of this, but there are lots of papers that are sort of referred to in the talk here, which deal with different aspects of the privacy technologies we have dealt with. So we took sensor data and we sort of have the system called PEIOT. What it does is it essentially injects privacy mechanisms based on the organizational policies into data. So when the sensor data flows in, the privacy technologies are sort of called, maybe it's differential privacy or encryption or randomization, and this produces what we call data products. And there are mechanisms in which people can use to opt in or opt out of these data products. And they can also sort of, there's a verification mechanism to see, the users can check whether or not the organization or the data collector essentially adhere to their policies or did not adhere to their policies. So with this PIOT, if you think of applications such as social distancing or occupancy or crowd flow, we can actually provide privacy in the context of build such applications with privacy intact, because The example that I was showing you earlier of occupancy, the determination and social distancing, the data being used there is anonymized data completely. So in this particular case, the data being used is actually randomized every 5 minutes, and the occupancy maps are built on top of such data. We could also have a mechanism of doing differential privacy and sort of build similar maps using differential privacy as well. But however, if you sort of go after location tracing or exposure tracing, then you have to have different protocols. So I'm not going to go into the details of it, but basically we designed a protocol which is similar in spirit to what I think Giles presented. Actually takes inspiration from that, but basically figures out a way in which we can track individuals create a protocol so you can track, let's say, infected people in locations where infected people visited without revealing their identity. And likewise, people can check whether or not they've been exposed, again, without revealing their identity as well. I think with that, I will end the talk and sort of give a thanks to the large team of people who have actually helped build this. So this is the team of people who have built in Tippers and in TICO, which is the system that we are building right now. There have been contributions to the different components of the system from a variety of different, let's say, partners we have had, including several companies and several different organizations. And the last thing I want to say was that the technology that I'm talking about is now being tested and for deployment in the Navy as well. Thank you.
All right, thank you, Sharad. So we're almost on time. That's a lot of information to fit in a session. I would like to invite all the panelists to turn on their videos now, the panelists in that session. So there are a lot of Q&A going on. I encourage all of you to go and answer the questions to you afterwards. What I'm going to try to do next is I observed some commonality in the questions, so I'm going to only ask those questions that they were the most popular or apply to most of you. So one popular question was about inclusivity. All the solutions are great, but they assume that people have smartphones. So I know this is a very high level question, but it's a legitimate question. So do you wanna, I would like to hear the thoughts of each one of you. So Giles, do you wanna go first?
Yeah, this is a very legitimate question. When I said that we try to be as inclusive as possible, I was talking about older and cheaper Android devices, but we're also thinking about ways to deploy the system in an even much cheaper way using low-cost wearables. And so that's an active effort that, you know, could we deploy exposure notifications using a $10 wearable that could be subsidized? So yeah, it's definitely an issue that we're acutely aware of.
All right. Pablo?
No, the same. I mean, I've seen some solutions around wristbands and wearables that you hand. Not the most convenient, and sometimes you need to self-identify and fix the battery issues. I'm seeing it in private settings like corporations and more controlled environments. But I think the important thing is on the mobile phone adoption that you know, the features that are released both on Apple and Google, that they try to cover the largest amount of customer base, and also for devices that are you know, Huawei or Xiaomi, that are they have their own implementation and support of some of the features of Android that also gets supported, and that there is no problems on the interaction between this push notification and those devices. So I think there is room for improvement there, but the wearables still a large space that will probably come when prices come down.
Yeah, and just to mention, that was behind the design decision to ship exposure notifications in Google Play services rather than in the Android OS, because that allows us to backport it to much older versions of Android.
Ramesh, are you ready or you need more time?
Yeah, I'm here, but I cannot start my video for some reason.
That's fine. You have thoughts on the inclusivity part?
Can you allow me to start my video? Because it's been
Yes.
stopped by the host. So yeah, I think that's a very important question about inclusivity, and I think that's why emphasis on a single approach is completely kind of mispositioned. So at PathCheck, for example, we think that even a simple QR code at a site can play a big role. So we have a very nice team from actually Africa, from South Africa, that has merged with PathCheck called COVID. And using QR code that are disposable, one can join, even if you're a homeless person without a phone. If you go to a particular public location, it can be tracked. And as I said earlier, I think GPS can play a very important role, because even a society that has, let's say, only 20% smartphones, an individual who goes to a particular wedding or a grocery market, and later on contact tracing figures out that this person was at risk, the town can just publish a map, very much like a weather map, at a 7 o'clock news or in their newspapers the next day, and alert everybody else. So I think, as technologists, I'm very excited about Bluetooth. Actually, when I took a leave from MIT, I went to Facebook and started a group on Bluetooth-based contagion analysis. And so as a technologist, I'm very excited about it as machine learning and a crypto enthusiast. But I think the solutions some of them are very low-hanging fruit. And we want to make sure as a community, we don't drop them.
Right. Sharad?
So I would agree with what Ramesh is saying. I think as dependence on a single technology is sort of fraught for danger. And I would also want to pitch in for continuing with the thought process a bit more. So this is exactly the reason why organizational approach sort of makes sense to me a lot. Because imagine if you think of, let's say, shopping complexes, malls, buildings, whatever it is, whether or not you have Wi-Fi in almost every, it's ubiquitous. Now, again, Wi-Fi also depends at the end of the day on the people carrying smartphones or having some kind of devices or the other, right? But there are cameras as well. So having an approach where you can sort of leverage all these different sensing technologies to sort of create a much more, let's say, robust representation of occupancy and so on would be a very useful tool for that matter. So the other thing which I wanted to sort of push and maybe ask further would be the following. So this is true that adoption and the aspect of having, let's say, penetration of, let's say, number of people having devices and so on. But the other aspect is, to what level should adoption be for these tools, any of these tools to be effective? And that's a larger question to me that maybe we cannot save everybody, can we save some? That make sense?
Yes, I had this in my next questions actually. So what is the,
All right, I jumped it, I guess.
Well, actually, as a follow-up to that, so what is the right level of deployment and scope for such an app? Is it campus-wise? Is it country-wise? Is it worldwide? So what is the right level for the contact tracing apps? Pablo, I'm gonna start with you this time.
Sure. I mean, so something that's happening in Europe, these contact tracing apps are very much depending on the national health authorities. So there is one per national health authority, pretty much, because they have to be integrated into their tracing system. But that doesn't mean that they cannot be interconnected at the national level. So at the EU level, there is an effort to integrate this month a number of countries coming together, because eventually there's going to be mobility opening up and there's going to be roaming. So regardless of where you live or where you go, you should be able to get notified if you're being exposed. So I think we're going to see more of this interoperability across these different apps being deployed. In terms of adoption, I still haven't seen real deployment numbers. I mean, I think it's still too soon. The numbers that we're seeing are, Germany has more than 10 million, and in the UK, they started with a very good start. In Spain, it's about 4.5 million, but it still is not enough time to gauge the true efficacy of these apps. I've seen simulation studies. I think there was some report by Oxford saying that they at 60% of deployment that probably an app could deal with a lot of the pandemia. And I think a lot of people stuck with that number, but I don't think there is a threshold. It's not on and off. It helps at different stages and different levels, and every life count. So I think the important thing is to go for adoption and make sure that there is a sustained effort over time. So they keep helping as much as they can.
Yeah, I think.
Athina, you're muted. Athina, you're muted.
All right, so Pablo thinks it should be at the global scale, interoperable at the global scale. Sharad thinks it should be very organization specific. I will take one more opinion on that. Giles, do you have any perspective on?
I think, just practically speaking, it's very important for these systems to be run at a government level. You know, just in terms of the infrastructure required to deploy them. And so, like, whether that's a state government or a national government, I think that doesn't matter. In terms of the adoption rate required, we also saw that 60% number that Ramesh mentioned, and we've been talking to the Oxford researchers about that, and actually, you know, it was misinterpreted, and there is not really a threshold under which you don't save any lives. And actually, the sort of the ramp up point is now thought to be around 15%, to my understanding. So it's a lot lower than that.
Yeah, I think that there's. Sorry, go ahead, guys.
Yeah. One other point. Oh, sorry. Go ahead.
No, please finish off.
One other point I wanted to make is that there are some niche environments where a tailored solution in something like ultra wideband is appropriate. So, for example, inside the workplace or in a corporate environment, there's very different solutions that can be deployed, and some of the wireless-based solutions that Sharad mentioned are also appropriate within smaller organizations.
Yeah, I would say, I think the question, I agree with Pablo and Giles and Sharad, and this point of whether should be regional or global interpolation or should be done by health authorities. I think they're all the right points. At the same time, frankly, we don't know the answer, right? Because we love simulations. All those papers are based on simulations, but all simulations are doomed to succeed, right? And they'll give you the answer that the simulation really give it to you. I mean, at 60%, square of 60 is what, 0.36. So 36% of encounters are captured. At 15%, only 2.25% of the encounters are captured. So, but statistically, that would mean nothing. 2% encounters captured, but in reality, the world works in a click, right? A lot of people are together, as opposed to everybody meeting, the probability of everybody meeting everybody else in the town. So if you're on a campus, even if rest of the city doesn't do so well, if the campus has really high density of adoption, that works out really well. Nevertheless, I think the point again is a single mechanism like Bluetooth is the wrong way to think about it. And given the theme of this workshop on privacy and contact tracing, I think now is the time to start allowing every other modality, GPS, Wi-Fi, UWB, why not? For asset tracking, and the algorithms already exist. We can use them in extremely privacy preserving way to deploy them. So again, not to put guys on the spot here, but right now, if you think about GPS, the apps could record the GPS on the smartphones, every 5 minutes, and just keep a local secure log of them, as opposed to the way the apps work right now, which is GPS is more of a app level functionality as opposed to an OS level functionality. And if they're encrypted, then an infected person who just talks to the contact tracer and that information comes from any other source. It could be verbal or something, and an alert could be sent to everybody saying, for your secure encrypted GPS location, here is an alert we can send you. Of course, the accuracy is not going to be as good as other proximity technologies, but based on your symptoms and ability of testing facilities, here's the best thing we can do. And we can move much faster and create tools. And the flip side of that, again, is the Bluetooth-based solution does so little for public health and businesses because they don't see a dashboard of where all the hotspots are and where the activities are and how the trends are changing. Again, from a privacy preserving, from crypto point of view, the solutions exist with multi-party computation, with split learning and so on. And we do have one solution coming from Google using MPC for a number of exposure notifications. So that's exciting. But that again limits you to exposure notification part of it only. If you look at the apps that have come out from Pennsylvania and New York, it's a little bit shocking because unfortunately they have so much invasive telemetry built into it that they're just going to suck up all the data about your age and your ethnicity and even your sexual orientation, suck up straight from your phone to the servers being run by companies in New York and Pennsylvania. They're completely flouting the original intention of the Google Apple exposure notification protocol. And somehow, the governors are coming on the screen and asking people to download these apps. I don't get it.
Actually, if I can add to what I think Ramesh is saying and maybe ask a question. So I think the concept of privacy in the context of, let's say, the kind of things that we are talking about is quite well developed. There are mechanisms for differential privacy, there's MPC mechanisms, secret sharing mechanisms, whatever it is, split learning, all that stuff is sort of applicable. And the larger question to me is, I think Giles had this in his slide, one of his initial slides, which is false positives and false negatives. What's the definition of contact? Is 6 feet, 15 minutes? Is that the answer? Is it 7 feet and 25 minutes? Because it depends, in this particular case, depends on whether a person is speaking or not, if he's shouting or not, if he's singing or not. So it's complicated. Like, how do you control essentially the rightness of any technologically, the correctness of an accuracy of a real contact? That's sort of difficult that seems to me like a very fundamental problem we have to address somehow or the other, in addition to sort of privacy, which is an easier here problem, it appears to me.
All right. I hate to cut down the discussion, but I have to. So thank you, everyone. It's time for a 10 minutes break. I'm going to leave the link open and we'll come back to the next session, which partially overlaps with the topics here. So some of the things you mentioned, we'll continue to discuss them. So thank you, everyone. And we take 10 minutes break.
Thank you, everyone.
Thank you.